Welcome to our lecture on polyalphabetic ciphers. So to introduce this lesson, what we're going to be talking about, we're going to be moving beyond simple substitution ciphers. We'll talk about the weaknesses of monoalphabetic ciphers. You've seen them already. Introducing multiple alphabets for encryption. And we'll talk a little bit about the historical significance in cryptography. So some of those limitations of monoalphabetic ciphers are each plaintext letter always maps to the same ciphertext letter. So that makes them vulnerable to frequency analysis. Even long ciphers can be broken with time and effort. So as you've seen the previous lesson, monoalphabetic ciphers are very easy to break. Even a long cipher could be decrypted given a little time and several people. So how can this be harder? How can we make it harder? One way is to use more than one alphabet, switching between them systematically. This type of cipher is called a polyalphabetic substitution cipher. Poly is the Greek root for many. The difference, as you will see, is that frequency analysis no longer works the same way to break these. So let's take a look at one of the most well-known polyalphabetic substitution ciphers, the Vigenère cipher. It encrypts each letter of plain text with a different Caesar cipher. The Vigenère cipher is a polyalphabetic substitution cipher that uses a repeating keyword to determine how each letter is shifted. Let's restate this using specific terms that we've learned in the last lesson. So in a Vigenère cipher, the algorithm is a polyalphabetic substitution cipher that encrypts a message by shifting each letter of the plain text by a different amount, which is determined by a repeating keyword. The core of the algorithm is the use of multiple Caesar ciphers applied in the sequence controlled by the keyword. The Vigenère cipher uses a 26 by 26 table with A to Z as the row heading and column heading. So there's 26 different alphabets. This table is usually referred to as the Vigenère table. The first row of this table has the 26 English letters, starting with the second row. Each row has letters shifted to the left one position in a cyclic way. So for example, when B is shifted to the first position on the second row, the letter A moves to the end. Go back, you can see that. The second row, right, shifts by 1, so it starts with B and goes to C. The third row shifts left by 2, C to Z, and then AB. The pattern continues until all the 26 shifts are represented. So each row represents a different Caesar cipher. In addition to the plain text, the Caesar cipher also requires a keyword, which is repeated so that the total length is equal to that of the plain text. For example, suppose the plain text is "all is not lost" and the keyword is "dog." Then the keyword must be repeated as follows. Well, you can see it comes to "all is not lost," "dog do," and you can see it on the screen there, okay? We follow the tradition. We'll go back a little bit. We follow the tradition by removing all spaces and punctuation, converting all letters to uppercase, and dividing the result into 5-letter blocks. As a result, the plain text and keyword become what you see on the screen there. All is not lost, broken up into 5 characters, 5 characters, and then the final 2 characters. To encrypt, we want to pick a letter in the plain text and its corresponding letter in the keyword. Use the keyword letter and the plaintext letter as the row index and column index respectively. Say that again. You want to use the keyword letter as the row index and the plain text letter as the column index. And the entry at the row column intersection is the letter in the ciphertext. For example, the first letter in the plain text is A, and the corresponding keyword letter is D. This means that column A are used in the row of D, and the entry D at the intersection is the encrypted results. So, as we keep going forward throughout our plain text letter by letter, here's our plain text, here's our keyword, and there is the ciphertext. Each plain text letter is encrypted with a potentially different alphabet depending on the corresponding keyword letter. You can see in this example how much more difficult it is to see frequency patterns, right? So plain text letter L is represented by Z, R, and then R again. Plain text letter S is represented by two letters, H and G. T is represented by two letters, H and Z. Ciphertext letter H then is represented as plain text letters S and T, so on and so forth, and it goes on and on. So over time, cryptanalytic techniques, it's easy for me to say, right, have exposed weaknesses in classical ciphers, leading to the development of more secure encryption methods. Next, we build on what we did a little bit ago with frequency analysis to outline a few other types of attacks on these ciphers and explain how their weaknesses led to improved cryptographic techniques. The first one is brute force, right? We're trying every possible key until we find the right one, okay? If the key space is small, a Caesar cipher, right, with only 25 possible shifts, an attacker can systematically test all keys. So what did we do to counter that? We use a larger key space or increased key complexity. And it works on Caesar, columnar transposition, rail fence, and Visionaire if the key is short. We'll summarize all of these at the end as well. Frequency analysis is studying letter frequency patterns to break substitution ciphers. We've seen that in the previous lesson. How it works is that certain letters appear more frequently in a language, right? E is common in English, vowels, ST. So if a cipher does not disguise letter frequencies, an attacker can match them to known distributions. Counter that, we use polyalphabetic encryption, like Visionaire we just talked about. Or randomized substitutions. So frequency analysis works on Caesar ciphers, Polybius, it doesn't work on columnar transposition, sorry. And it works again on Visionaire if the key is short. The next one is an anagramming attack. It's rearranging letters in ciphertext to reveal plain text order. Since transposition ciphers shuffle rather than substitute letters, an attacker can reorder them by recognizing common words or letter patterns. So to counter that, we use multiple transposition rounds or mix with substitution. Anagramming works with columnar transposition and rail fence. Pattern recognition attack is identifying recurring structures in ciphertext to guess the encryption method. Some ciphers, like rail fence, introduce predictable letter spacing, which can be analyzed to determine how the encryption was implied. To counter that, again, we use irregular patterns or additional encryption layers. Rail fence is what pattern recognition can work on. Our last one is the Kosinski examination, which is finding repeating sequences in a polyalphabetic cipher to determine the key length. It works so if a key repeats, as in Visionaire, it does, certain plain text segments will be encrypted the same way, allowing an attacker to estimate the key length and eventually break the cipher. We can counter this by using a long, non-repeating key, like something called a one-time pad. And again, this process works on the Vigenère ciphers. So you can see the summary here of each attack type. I won't repeat them. What it does, give some time to look at the summary table, the countermeasures, and what ciphers each of those attack types work on. Okay. These methods of attacking ciphers is what has led to further development of them. So for example, Polyalphabet's susceptibility to frequency analysis encouraged homophonic substitution and fractionation techniques. The Ciphers vulnerability to brute force and frequency analysis led to Vigenère and eventually to the one-time pad. Rail fences flaws inspired the development of irregular transposition schemes and block ciphers. Columnar transposition weaknesses contributed to product ciphers, which combined substitution and transposition, like AES. And Vigenère's weakness against Kasinsky's attack pushed cryptographers to develop stronger randomized encryption methods. These discoveries led the groundwork for modern encryption that we learn about in the next lesson. So what are some of the takeaways from this lecture? We should remember that polyalphabetic ciphers significantly improve on monoalphabetic security. The Vigenère cipher uses multiple Caesar ciphers controlled by a keyword. Each plaintext letter can encrypt to different ciphertext letters. The repeating keyword creates a pattern that is still vulnerable. And this has all led to the development of more secure cryptographic methods. Now, here at the end, we have a neat little video on decrypting Vigenère, and I hope that you get a lot out of it and enjoy it.